Hello everyone. So today I want to talk about streaming and how to use streaming to solve data problems. And we're going to talk about microservices, POP and SAP, and Kafka, and how to use this stack to solve real-world problems. So I'm Thomas Neubauer. I'm CTO and co-founder at Quix, and previously I worked in McLaren, where I kind of get to the streaming. The way how we get to the streaming was that we were connecting F1 cars to the cloud, so people in factory can actually build a decision insight on top of data live, real time. I was leading the team, and we quite quickly found out that a database-centric approach is not going to work, chiefly because the amount of data were enormous. It's roughly 30 million values per minute. Some of the sense data, like a vibration on a gearbox, sends 4 kilohertz data, so 4,000 different numbers per second. And so we basically end up using Kafka, and then we were building a platform to use that know-how outside of motorsport. This is where the founding team met, and we got the idea that maybe this is a good opportunity to build something to make this easier. So let's talk about streaming and what actually that means, and how the streaming different from batch. So I quite like the something happened with the projector. This is not how it should look like. Okay, now good. So I quite like the analogy of water. So imagine you have a garden with the flowers, and you need to water them, and so you have a river close to your house. So if you're going to use batch system, you're going to get the bucket, you're going to go to the river, fill the bucket with the water, go to your garden, and water your flowers. Now, that means that you have to wait to fill your bucket with the water, and so there's a gap between your flowers being watered and being on dry. Streaming, on the other hand, is where you just build a pipe from your river straight to your flowers, and they are being constantly watered. Now, in a data, that means that basically streaming is about processing piece by piece data as they're coming from the source. And batch is, as you probably all of you know, is taking a batch of data, frame of data for some period, and doing the transformation. Streaming also requires a bit of a change in mindset in how you build your architecture. So we are not putting database in the middle and the center of your architecture. We are rather putting it on site, and we're putting a broker in the middle and the center of your system. So this is a traditional batch approach. You send data from your data source to the database, and then you have some big data tool like Spark to load the data into the Spark, do some transformation, and then you put it to some other database, maybe the same database, and then you put a dashboard on top of that. In streaming, we still have a database, and database is still very crucial technology in streaming, but this time it's just serve the purpose of persistence. So we save data for later, for analysis. Maybe we want to do some aggregations later, or maybe we want to just explore what happened yesterday or the day before. But the actual transformation happens in memory. And we use Kafka broker or any other broker to build microservices and connect them with a broker to talk between each other, and creating pipelines like this. So here we send the data to the broker, which is the first arrow. Then we have a microservice that subscribes for the data, adds a feature, and that feature is then consumed by another microservice, which is the real-time dashboard here. So this is basically one-on-one of streaming in terms of architecture and the whole idea. So what is our approach? What are we trying to do in Quix? Well, we're trying to combine Python, Kafka, and Kubernetes to solve streaming, to help people solve streaming problems with those technologies. Why Python? Well, because Python is quite a nice ecosystem and community with the different data libraries. ML words living really there. There's lots of physics and mathematical stuff there. And it's easier to use than maybe, for example, Java, which is a language where most of the streaming technology is built, and therefore quite often you will find a lot of technologies using Java and really requiring people to use Java to use the streaming tech. So our idea is that we build pub and sub services around Broker, and we use Python to do the data transformation. There is no server-side logic, like for example Flink, that you probably already heard. It's just using Kafka and Kubernetes together in a marriage to scale and build a resilient system for you. Now, what that really means. So the most important concept to grasp is pub and sub service. What that means? Well, you send data to a topic in a broker. Topic is like a pipe, one of the pipes in your system, and your microservice, it's too much, your microservice, which is the rectangle in the middle, subscribe for the data, and in memory, doing the transformation in Python. That could be a very simple normalization of data. It could be cleaning your data, filtering, up to calling an ML model to do to use machine learning. So really, flexibility is there. Now, how this scales and why this actually works? Well, first of all, the input topic, and actually every other topic in the broker, is actually composed from tiny, smaller topics. We call them partitions. Those partitions are redistributed over the cluster. And when you send data to the topic, this data being equally shared over those partitions. That means that if you get more and more data, you're just adding more nodes into your cluster, and this is how you horizontally scale pretty much infinitely. Now, it's also built a quite resilient system because you can set replica to your data, and what that means is that Kafka will send everything twice, maybe 3 times, into different partitions. So if you have a hardware failure in one of the nodes in your broker, processing is still ensured. And then the scalability of your compute part, when you're actually doing some transformation, maybe you're calling your ML model, we use Kubernetes replica system and Kafka consumer group system. How does it actually work? But those partitions that are now sharing the load of your pipeline are being equally redistributed over different replicas, different instances of your service in this consumer group. So if you're going to have, for example, 100 devices sending data, and you're going to have 10 partitions, in each partition you're probably going to have roughly 10 devices. And if you have 3 microservices, each would roughly serve 3 or 4 partitions, so 30 to 40 devices. And this is how you can scale this, again, up to massive numbers. It is also very fault-tolerant architecture. So we already discussed how fault-tolerant is the transport of your data. So if something in broker, some hardware failure happens, there's an application. And if there is a problem with your compute, with your code, maybe you have bug in your code, if one of the services crash, it gets immediately restarted by Kubernetes. And if it takes time, others will take the load momentarily to ensure that there is no downtime. Also, Kafka have a queue system, which means that if you have a downtime, Kafka would remember where you stop processing your data, and next time you restart, it will start from that moment, so there's nothing lost in the process. So that's also quite good if you, for example, have more data than you expected, and your clients are not served immediately. They will just be served a bit later. There's no client timeout like in API-driven architectures. It's actually quite resilient for peaks during the day. So this is a theory. I hope it wasn't that complicated. You can ask me at the end if you have any questions. But I want to show you how this actually looks like in reality. I think I have, 15 minutes. So I'm going to show you how to build a very simple pipeline with my phone and with my computer right now. So I have a phone that I'm going to convert right now to an IoT device. This phone is going to send telemetry data like temperature, location, speed, and G-force sensor, acceleration sensor from all dimensions into a topic called phone data. And we're going to build a super simple service that's going to inherit from this data a new feature which is calculating a total amount of forces applied to this phone from all dimensions. And then we're going to consume it. It's super simple dashboard, built-in dash. So I'm going to switch to Quicks and maybe try to make this like that. Cool. Hopefully I'm not going to damage anything here. Yeah. So basically, this is Quicks. Hopefully I'm gonna have internet. Cool. So I'm gonna start my phone and start sending some data. And cool. So here we have a topics. So as I told you before, this is like a pipe, two different pipes that we have in a system. And if I go to phone data now, you can see here my Thomas Samsung S20 phone. And if I shake, you can see it auto reset because I have changed the data, and it's now sending all 3 dimensions from the sensor real time from my phone to this broker in the cloud. Now, obviously, when you do this, you want to understand the data a bit. So this is where the database comes into the place. I'm going to go to topics, and here I have my persistence enabled on this topic. What that means? Well, that means that this topic is also synced to database, so I can analyze the data. So I can go to Quicks now and see that I have done this quite a number of times already. And if I check this one, this stream, you can see that, yeah, yesterday I was sending some data. I can also, for example, get this into Jupyter Notebook and do some analysis. So I would not get the exact same data that I sync waveform in the Panda data frame in the Jupyter Notebook. And I can do analysis, understand what is coming from the phone, so I can build real-time pipeline. So let's assume that I understand now what I want to do. Then I go to our library. This is actually quite crucial part of streaming and building microservices. There's a lot of legwork involved in building our microservices. So what we have done is like a microservice generator. You choose a template, you answer some questions, you tell it when you want to get your data, when you want to write it, and it will generate the whole repository with everything you need to work out of box. In this case, I'm going to use pub and sub template, because we are going to create a pub and sub transformation. And the whole repository includes things like Docker file and requirements for dependencies. You don't have to really worry about that, but you can edit it later. What is important is this function. And this function basically just what it's all about. Here, I'm not sure how we can read it, but this is just a method where we're going to get a Panda data frame. We can manipulate with the data, and we then send the Panda frame back to Kafka. That's it. So I'm going to create this microservice, and I'm going to call it a GeForce Total. So I'm going to listen to phone data, and I'm going to output it to GeForce Total topic. Cool. So now this microservice is generated. I have a Git repository I can clone and do it locally if I want to use IDE, PyCharm, whatever. Or I can use this web IDE here with a Kubernetes-powered development environment if I want to save some time. So I will do that. And here, in this method, I'm basically just going to do df equal data to Panda frame, and I'm just going to print it. So we see that it's working. So if I press run, now I'm going to run this microservice. It's going to subscribe to the data coming from the phone and others if I would have more phone here. And you can see I'm getting data frames in a memory, and now I'm free to do whatever I want. So I'm going to take 3 columns from this data frame and calculate a new one. So I'm going to stop this, and I have here code snippet to save some time, but you will see it's a very short one. So there we are. If there is a GeForce data in the frame, I will just calculate the absolute value of all dimensions into one value. And then I press run, And as you can see in the console, we have 10G applied to this phone, which is the gravitational force of the Earth. And if I do some shaking, it's going to 20 because I'm moving with it. So now we have solved this problem, and now is the time to deploy this. So you can see here that we have a output coming from the service, and it's like a one kilobyte. So I'm going to stop this, press deploy, and here I'm going to deploy it into Kubernetes as a container. So it's going to be service. I'm going to give it 1 core, and I think that's it. Cool. So now you can see that this pipeline is actually starting to look like what we had in the slides. We have a phone data, we have a microservice doing some transformation, and now we're going to add here the dashboard. So there's many ways how you can consume your data. It doesn't have to be dashboard. It could be database. It could be your product. So you can go and send the results back to your product, like shopping recommendation. Or you can, for example, raise alarms. You can send Twilio message. You can send email. You can basically react and automate reaction on your data. So you don't have to look at the dashboards all the day. You basically do what the person would do when found a problem in the dashboard. So now I'm going to put here another template called real-time dashboard. This is using Dash, which is like a Python library to build dashboard without knowledge of JavaScript. It's quite cool. And I'm going to listen to GeForce Total. I'm going to save it as a project. And here I'm not going to do anything. I'm just going to be basically, just going to get rid of this. Data.df. There we are. And this is now installing under the hood Dash and all the libraries that I have in this template. It's take like 15 to 20 seconds. Should be there soon. Yeah, there we are. And now, when it's finished, yeah. And now I'm going to run this. And this will also give me an address, which I can open in a browser. And if I click here, there we are. So now you can see that this dashboard showing the last values from that function. And how this actually works. Well, that microservice is getting the data from the broker into memory. And we have what we call in-memory view. This is the data being basically accumulated in the memory of the microservice. And this dashboard is just reading it. That's it. And I hope that it makes sense, or at least partially. And if you want to give it a try and play with the streaming, you can basically replicate what I did today. All the code is on a GitHub, and many more examples. And you can even get this QR code to sign up to get more credits if you want, and play with the streaming and microservices and everything. So thank you for being here, and if you have any questions, I'm here. Yes?
How do you send actually the data from your phone to other exposed data from phone to an app?
Yes. Yes. So I have a very simplistic app that's reading the sensors and using WebSocket connection to send into our gateway service, which is one of the services you get out of box in Quix, and that is sending data to broker.
I have a question about processing. Assuming you have a streaming at 1 gigahertz, I believe that you have to process data faster.
Yeah.
Right? Otherwise, you're going to have like a bottleneck in your pipeline, and you're going to lose some data at some point.
Yeah.
How does it work? How do you make sure that you process data faster with respect to how fast it comes in?
Yeah. So it's a kind of a monitoring issue. So what happened in streaming with the Kafka, if you are not giving it enough resources to process it real time, is that you're going to start falling behind the leading edge. So basically what's happening is that what your service is processing is not now, but what happened 1 minute ago. And this is a delta that you need to watch out. And obviously, if you see that, you just increase the resources on your processing. You maybe horizontally scale it to get more instances and more resources to catch up with the leading edge. What also quite often happens is that when you have a downtime, then your processing would start to catch up with the leading edge. And this is a moment where quite often you're going to need a bit more resources to catch up with the leading edge and get there. Yes?
Basically, I mean, this technology for processing large amounts of data. And you're using Python and doing like record after record, row after row processing. Like, with Python, is that? I think that's not very efficient.
So first of all, you don't have to use only Python. So we right now have a C# as well, and we're going to use other languages very soon. The reason why we talking about Python in the first place is because Kafka as itself is very efficient, and this whole idea is super efficient way of doing it. Yes, the Python gives you a bit of a performance cut, but what you gain with the Kafka is much more. And if you want to get it really, really efficient, then yes, you will switch from Python to something else. But we also do a lot of improvements in the performance under the hood. So for example, we're using protobuf binary format. We're sending data incrementally. So imagine you are in a car doing 100 kph. We are not sending 100 kph JSON every second. We're just sending delta between the numbers. And we are not handling data as a key value message, but as a scalar value. But those improvements mean that, for example, comparing with the Spark to do the same job, it's around 80 times better in memory and many times better in CPU. So actually, even with the Python, you save lots of money. Yes.
So for the Kubernetes cluster, what are you actually using behind the scenes? Are you using like AWS, or do you have something set up on your own? I'm just wondering, when you set the CPU and memory, what's actually happening there? Do you call the API and start new things? Or?
Yeah. So the way how it works is that right now what you saw this managed service running in Azure, but in AWS it's basically the same, just using AWS services. It's a Kubernetes cluster. And what we do under the hood is that when you press deploy, it goes to what we call build service, when we take the code and Docker file and we build a Docker image. And then we call Kubernetes API. We point to that Docker image with the Helm chart and deploy it to the Kubernetes cluster. And then we're monitoring the logs and the CPU and memory in that cluster. Yes, so it's a multi-tenant cluster. So we're using Kafka and Kubernetes in a multi-tenant way, which means that we can put all the customers on this big cluster and manage it. And when you set to CPU, we just limit on a container and place it to the right node in a cluster. Yes?
Can you mention like one big surprise or difficulty that you had like while building this? I really love the presentation, and thank you for that.
So difficulty obviously comes with Kafka. So Kafka, although it's a very powerful technology and you can really achieve interesting results with it, for management and configuration, it's a monster. And that's why we built the Quicks. It was built with a little effort to end users that configuring it. So we had some quite incredible problems with Kafka at the beginning. We also had to solve some problems with Kubernetes and networking. Cloud providers are not perfect. They have their problems. So there's also value in managed serverless offering that you don't have to do that. The company do it for you.
I also worked with Julie-Wolfthorn-Str in the past with IO. I mean, I think summarizing, aggregating is easy and easy to explain. What I found most challenging is how to apply that to machine learning problems. I mean, I know also that there's streaming ways to accurately count unique users, count sketches, for example, something like that. Like, do you have more examples? What do you?
Yes.
I think this is really the aggregations, good example, but what else is possible?
So there are two. So I'm quite often using a sentiment analysis as an example on our conferences. So that you have a chat room and you're sending messages to the topic, and then you have ML model listening to those messages, calling the ML model for sentiment in the message, and you're outputting score. So this is an example when you use ML. And the second question was?
Example, like, content sketches, like,
yeah, okay.
Stuff like
yes, so then you have what's called stateful processing. So that's actually like the most difficult. Well, it's the cherry pick on a complexity in streaming. So stateful processing is when your microservice accumulates some state, and you're basically nurturing that state with your live data. We do it in Quicks as well, and the way how it works is that when you checkpoint your service to the Kafka to tell Kafka, I have processed up to here, we offload the state to the disk. So we are not doing it every message, that would just kill the performance. We're just doing it once per 20 seconds. And if you have a restart, you get back to that checkpoint, you load the state, and you continue. So for that, you can look at for example, a stateful processing library item in our platform. There's an example how to do that. Cool?
Any more questions, maybe?
So thank you very much, and hopefully you like it.
Thank you very much, Thomas. Impressive one. Thanks.